All right, so we're going to pick up where we left off. Now we're going to talk about specific reaction mechanisms. And so a reaction mechanism is just a sequence of events that describes the actual process by which reactants become products. So you can think of the reaction mechanism as the pathway that the reaction takes. If you think back to Hess's law and you think of our master equation, and then we have the 2, 3, 4, 5 different equations below that, and we're manipulating them, so we flip them or we multiply by a number. Those equations that we manipulate, that's the actual reaction pathway. So those reactions aren't just random. Those are the reaction steps, or the steps the reaction takes to turn reactants into products. Don't think that every single reaction occurs in one step. So there's reactions that occur so quickly they could occur in one step, or we think they occur in one step, but in reality, a lot of our reactions occur in multiple steps. And so the reaction mechanism is simply the series of reactions that show the different steps the reaction goes through. So reactions may occur all at once or through several discrete steps. Each one of those steps is known as an elementary reaction or an elementary process. So that's very important to make note of. Each individual step in the reaction mechanism is an elementary process. Now, what does that mean? Let's see if it says it here. No, okay, so we'll go back here real quick. What that means, and I would write this down in your notes, elementary reactions or elementary processes are processes or reactions that occur in only one step. I'll say that again. Elementary reactions or elementary processes are reactions or processes that occur in only one step. And that's going to be very important for us as we move forward and to finish up this unit. So one thing we look at just really quickly, elementary reactions and the rate laws. So we're looking at the molecularity. So these are different examples of elementary reactions. Again, elementary means all of these occur in one step. And so we also look at the rate law. So there are a few things to point out. The first thing is the molecularity. The molecularity of a process tells you how many molecules are involved. So unimolecular means there's only one molecule involved. Bimolecular, 2 molecules. Termolecular, 3 molecules. And so you see here 1 molecule versus 2 molecules versus 3 molecules. And 3 molecules could be 3 of the same thing, or it could be 2 different things, or 2 of the same, 1 different, or all 3 different. So the first thing, unimolecular versus bimolecular versus termolecular. The next thing to look at here is the rate laws. So we see the rate laws. So we see this is rate equals K times the concentration of A to the power of 1, A to the power of 2. The one thing that I want to point out here is what you should notice here is that the rate law, or the exponent, is the coefficient from the balanced chemical reaction. So if we look here, this A, the coefficient in front of it is 1, and it's a 1 exponent. If we look here, we have 2 A's. We could also write this, instead of A plus A, we could simply write that as 2A. And if we wrote that as 2A goes to the products, then that would be A squared. And so you see here 1 and 1, so the exponent is 1 and 1. So the thing to note, and I would write this down somewhere in your notes, the big thing here is when we look at elementary reactions. So I know before today I've told you don't assume the coefficients are the exponents, and we looked at certain examples. Well, if you have an elementary process or an elementary reaction, meaning you have a reaction that occurs in one step, the coefficients from the balanced chemical reaction are going to be the exponents in your rate law. I'll say that again. the coefficients from your balanced chemical reaction are going to be the exponents in your rate law. And we know that the exponents simply tell us the order of the reaction. So if you have, and again, this is only true with elementary reactions. If you don't have an elementary reaction, you can't just pull the coefficients and make them the exponents. However, if the question tells you that it's an elementary reaction, you can then use the coefficients as the exponents. And so you could look here, what's the molecularity of this process? Well, I have two molecules involved, so we would say it's bimolecular. And so we can look at multi-step mechanisms. So when we look at multi-step mechanisms, so the thing to understand here is that our chemical reactions can occur in one step, but a lot of them occur in multiple steps. They have multiple paths they take. So when we look at this, the first thing to make note of is when you have a multi-step process, one of the steps will be the slowest step. Just like if you've heard me play sports, you're only as strong as the weakest link. Right? I think in cross country, like we're only as good or we're only as fast as our slowest runner on the team. And so if we're looking at these two scenarios, you could look at cars. We don't have a lot of toll roads here, but you could look at these cars traveling through the Plaza A and Plaza B. So if the cars are slowed here at Plaza A, it doesn't matter how fast they can get through Plaza B. The Plaza A is what's forcing them to slow down, or is what is determining how fast they can move through these two plazas. Over here, if you look at Plaza B being the slow plaza, then it doesn't matter how fast. They can get through A as fast as they want, but they're going to get slowed up here. And so in this scenario, Plaza A is what's controlling the rate at which they can move through. Plaza B over here is what's controlling the rate. And so we look at the slowest step being the rate determining step. Again, remember what unit we're in. We're in the kinetics unit. We're talking about the rates of chemical reactions. How fast or how slow do chemical reactions occur? You can only move as fast as the slow step. Again, when you look at these two scenarios down here, the cars can only move as fast as the slowest plaza. So here, Plaza A, this would be the rate determining plaza, or the rate determining step. It's controlling the rate, or it's controlling how fast the cars can move through. Over here, Plaza B would be the rate determining plaza, or the rate determining step, because Plaza B is controlling how fast the cars can move through. So when we look at our chemical reactions, what we're really concerned with is which step is the slowest. After that, every single step is going to be faster than that. So we're not looking at what is the exact speed, right? We have one step that's slow, the rest of them are fast. So it's kind of like if you're not first, you're last kind of concept. If you're not slow, then you're fast. And one step has to be the slowest step. One person on the team has to be the slowest person on the team. So, and that's going to be the step that we are going to focus on as our rate determining step. All right, and so I'll go ahead and give a little preview, and then you'll watch these other videos later, but your slow step can either be the first step, so if the initial step is slow, or your slow step can be your first step is not going to be slow. So what we're going to look at two scenarios over this week. What happens when your first step is slow? You have a slow initial step, right? Initial's the first one. Or what happens when your first step is fast? How do we handle those scenarios? What information can we learn? How do we answer questions? And so we'll kind of dive into those here later this week.